Okay, good afternoon. I'll start immediately sharing the screen. If you go to our website, I have modified it here in such a way that all the recordings done over the last 2 years of the pandemic has been placed on the Illinois media space channels that you have access to just for your own information. Otherwise, we start our last lecture of the semester, and it's the continuation of what we started in looking at the risk of global climatic change. And I made the point last time that there are some drivers that are not under our control. If it is the solar phenomena, we cannot control it, and humanity has basically to adapt to it. However, there are options for us that we have under our control, and in that case, we should really intervene and face the situation so as not to get filters. And we identified filters in the paper that I asked you to read as what is called a gain of function research, which is a flawed logic of making natural viruses, say from bats, more virulent to attack humans, supposedly to produce vaccines against something that did not exist in the first place. The reality of it is that it's more like a way of producing biological weapons. So this is a risk that can end up society as we know it. People call it a filter. The other filter is obviously nuclear war. And the third filter that we are going to expand a little bit more on today is global climatic change. I connected here to global climatic change. And I would like to show you some of our own research here. It didn't need supercomputers to do some very interesting predictions. And you may find that the approach could be interesting for looking at other types of applications. So we talked here about the drivers for global climatic change. As I suggested, some drivers are positive in nature, meaning that they add, the name for them is radiation forcing from the Intergovernmental Panel on Climatic Change, that's IPCC. CO2, methane, hydrocarbons, nitrogen dioxide, N2O. This is released from burning fossil fuels in the same way as CO2. The ozone layer, all of these are positive forcing, but we also have negative forcings, like volcanic eruptions have a negative forcing in that they release dust to the atmosphere, they shade solar radiation. In addition, they also release sulfur dioxide, and sulfur dioxide apparently has the exact opposite of CO2. It leads to a global cooling. So now you have positive forcing, these are their error bars, and negative forcings. The cloud albedo effect is that clouds reflect solar radiation with a resulting cooling effect. The end result is that the positive forcings are win the case, and you could see that there is a huge error bar here, and we find that the net result is a forcing of about 1.5 watts per meter squared of positive energy being added to the Earth's atmosphere. Now, the question, of course, is what can we expect from that positive forcing? So this is some of our own research here. I'll let you read the rest of it, but I would like to come back to this later, is what's called the Great Ocean Conveyor Belt. Solar radiation, as it comes to the Earth, is definitely absorbed by the water masses, the oceans, and 70% of our surface of the Earth is covered by the oceans. So they have a very important role in distributing the heat energy from our sun. They have to interact with the masses, land masses on the Earth. And these are two descriptions of that circumglobal because it goes around the whole globe. And you notice that it has sometimes a red color, that is warm water, and sometimes it's a blue color, that is cold water. You could see here for the Atlantic Ocean that on the surface, the warm water finds its way up north along the coast of Europe. It warms the coast of Europe. And notice something very interesting here. If you take the same latitude as England, say, and you move here, same latitude, you'll find yourself the same latitude as northern Canada. So without that warm water in what's called the Gulf Stream, it was first studied by his name, Benjamin Franklin, that warm water keeps Europe in a climate that makes it really livable. If they didn't have that warm water, they would be at the same climate level as northern Canada under ice most of the year. Another depiction of that circumglobal current here in more detail shows it coming in here, coming in here, coming in here to the area of the Gulf of Mexico, and then it rises to the north. In the north, the warmth is dissipated, the water cools down and goes to the bottom of the ocean and returns back again. That's a cool subsurface flow and distributes the heat all over the Earth's surface. The interesting thing is that one single drop of water takes 100 years to make that big circle around the Earth. And I'll come back to this later on because this, the circumglobal current did not exist in that same way that we have today about 22 million years ago. So what happened actually 30 million years ago, that circumglobal equatorial current was able to move from the Atlantic Ocean, you could see here, through the area that is today Colombia and the Gulf of Panama, from the Atlantic to the Pacific Ocean. So it didn't have to go all the way. Some of it went to the Labrador region, northern Canada, but it didn't need to go all the way to Europe. As a result, the temperature from solar radiation on the Earth was distributed in a more even way. And being distributed in a more even way, according to our paleontologists and our geologists, it turned out that the Earth enjoyed a very nice climate in the sense that it was a temperate climate. Notice that at that time, Antarctica, which is now covered in some parts by 2 miles of accumulated ice in thickness, was open land. In fact, when they explored Antarctica, they found really cold there, and that meant that it had forests. And you notice that the Arctic Ocean here was open water. The area of Siberia also enjoyed a very nice climate. We'll come back to this later for 2 reasons. Suppose that we run out of options in terms of reducing carbon dioxide. So in that case, restoring the circumglobal equatorial current could save somehow humanity from the excesses of global climatic change. So how do we do this? We try to restore the same conditions that existed 30 million years ago by reconnecting the Atlantic Ocean to the Pacific Ocean. And that's a subject of a paper that I wrote with students, and I'll let you read it and write a summary about it. So that could be a savior for us in terms of a possible runaway global climatic change. If it's a runaway, it can lead the Earth to a situation like what happens now on Venus. Venus has an atmosphere that's primarily carbon dioxide, and it's so warm there that one of the probes that the Russians sent to Venus landed on the surface and operated only for 4 hours before melting. The temperature on the surface of Venus is such that it will melt lead. So that could be a saving approach to reconnect the Atlantic Ocean to the Pacific Ocean at the area here where they were interconnected 30 million years ago. And I'll even suggest that the level of the Pacific and the Atlantic are different because of the different salinities and the different evaporation rates. So in that case, you can even produce hydroelectric power from the flow from the Atlantic to the Pacific. So this was 30 million years ago. And notice again some other interesting pictures here. This is Mount Kilimanjaro in Tanzania. You see it has in Africa, it has an ice cap, and this is now the ice cap is disappearing. Not only that, but the Arctic Ocean, we know again that the Arctic is an ocean. You could see here the same date of the year from 1979 to September, the month of September 2005, that whole area here has now turned into open water. It is not ice like in the past. So that would allow us maybe to have a communication, open ocean waters from Canada and North America to Asia, instead of having to go all the way around the south part of the Cape of Good Hope in South Africa in general. All right, so we'll come back to this later on. It is no doubt that the carbon dioxide has been increasing in concentrations from, let us give some numbers here, 315 parts per million per volume. And these are measurements that happened from Point Barrow in Alaska. The Swedes had the plane fly up in the atmosphere. At Mauna Loa, there is an observatory on the volcanoes in Hawaii and on stations in the South Pole. Starting from the year 1660, you could see all the measurements there are basically agreeing that our carbon dioxide has been even not just increasing, but it has doubled in the concentration. And we'll take this into some kind of a way of making a prediction about the intensity of storms. That's two more recent graphs of that whole process. The curve is named the Keeling curve. Try to remember the name so that you can read more about climate science. Climate science is becoming a discipline now being taught at different departments in universities and geography departments and so on. But our interest in it is, of course, from the perspective of energy in general. You notice here that the carbon dioxide increases and decreases, decreases. It decreases over the summer when plant life in the upper hemisphere, of course, fixes the carbon dioxide through the photosynthesis process, and it disappears from the atmosphere. But in the winter, plant decay, bacteria turn back that CO2 back into the atmosphere. So you see the ragged curve here, but inexorably, it has been increasing from earlier on, about 315 parts per million into the level of maybe 390 or 400 parts per million per volume. No doubt, humans have added to the increased concentration of CO2. The pre-industrial concentration of CO2 is estimated as being 295 plus or minus 5, that's the error, parts per million by volume. In 1958, it had reached a level of 312 parts per million. And if you just calculate the relative increase, that would be, in 1975, it was 327 parts per million. The delta C, the change relative to the pre-industrial revolution, was 327 million minus 312 million. And that is basically 0.08, so 8%. The relative yearly increase, if you divide it by the number of years, which is 1975 minus 1958, is 0.0047. So this is a percentage yearly increase. Let me see if I can add. I have trouble doing it. Okay. So the yearly increase is about 0.5%. The relative increase from 1975 would be 0.1085. So that is about 10%, or let's say 11%. So we have been adding the anthropogenic. This is a human contribution to the carbon dioxide, an increase of about 10% per year here. Yearly relative increase from the industrial beginning of the pre-industrial age to the calculation 1975, because I have the data for that case, is 11%. What are the effects of that CO2 increase is debatable. People suggest that the temperature of the Earth obviously was going to increase, and the global temperature, the annual average, has been fluctuating. You don't feel it today, for instance. We have very cold weather, but we have volcanoes erupting in Indonesia. We have volcanoes erupting in the Mediterranean area, Mount Etna, I think, and then we have volcanoes erupting in Hawaii. So they are cooling the atmosphere, but that is temporary. They curved clearly on the 5-year average is increasing the temperature of the Earth. And the idea is it's attributable to what we call the greenhouse effect. And the greenhouse effect occurs with the different absorption bands in the atmosphere of the Earth. There are two frequency bands in the infrared. Infrared means in the heat part of the electromagnetic spectrum. We have some weak bands and some 15 micrometer, micro 10 to the minus 6 micrometer means 1/10 to the minus 6 of a meter of bands. This is their frequency. And you notice here in that graph that we can calculate the effect of the greenhouse effect here. If you start with a value of the carbon dioxide and you double it, the weak bands contribute, say, 0.3. That's a delta C degrees Celsius to the temperature of the Earth. But then you go up here and it is 1.5 degrees Celsius addition. If you quadruple the concentration of CO2 and CO2 here, we can calculate that you can increase it by 1 degree from the weak bands, and now another 3.5 degrees from the 15 micrometer band, then you end up with a significant increase, 4.5 degrees Celsius. From this, we can infer what would be the situation if you allow the carbon dioxide to increase in the atmosphere. And in that case, it will affect, of course, energy scenarios in general. You'll find that this is a 50 terawatt scenario of fossil fuel energy, coal, oil, and gas. And basically, you'll find that by the year 2100, you would be reaching a very, very high concentration of the CO2, leading to a very, very dramatic change in the Earth's atmosphere. So this shows us the carbon dioxide increase for a 50 terawatt fossil fuel energy scenario. What I would like to do is have you read the material, but then show you some actual computations on how what that can lead to. And the derivation is very simple, using basically a conduction model in the atmosphere. This is a composition of our atmosphere shown here as a function of altitude. You'll find that the troposphere here is just the region of the atmosphere where the weather phenomena are being formed. So you can see the clouds in the summer, the cumulus nimbus clouds climbing up into the troposphere. The troposphere is where the weather phenomena are made. In the troposphere, you can find the jet streams that move really most of the heat of the Earth. If you go up higher than the troposphere, you get what's called the stratosphere. And 30,000 feet here in altitude is really where airplane would fly. They fly in the troposphere or above the troposphere, they don't rise all the way to the thermosphere. They do not go all the way to the ionosphere. And notice here that as you are close to the Earth, the temperature is on the average plus 30 degrees Celsius. But as you rise up in the atmosphere, the temperature becoming negative here. So in fact, you can generate a graph of how the temperature distribution in the stratosphere looks like. Another way of describing the atmosphere is the troposphere is really the highest level that the weather phenomena or the clouds form. That's where commercial jets fly. Above this, basically, weather balloon can rise with helium. You have the ozone layer and the polar stratospheric cloud, and the density of the atmosphere is so low there that they cannot help airplanes fly. It's a very, very, very thin atmosphere. If you look at the temperature distribution, you'll find that the temperature near the Earth's surface is high. As you go up higher into the troposphere, we suggested it's at a height of, say, 10,000 feet, the temperature decreases and it goes back again into what's called the stratopause, and then decreases again into the mesopause, and then gets to the thermosphere. That's now where you have solar radiation, the temperature increases back again. We divide the atmosphere into those four regions: the troposphere, the stratosphere, the mesosphere, and the thermosphere in general. All right, so the idea here is to try to predict what happens if we change the temperature distribution in the atmosphere as a result of global warming. So in that case, we build a simple model, and you are all engineers, you'll understand what I'm doing here. I depend on a paper that used these graphs that I've shown earlier on when you double or quadruple the level of carbon dioxide in the atmosphere and how they would affect the temperatures. This is a paper from the IAEA bulletin. I couldn't find the date exactly, but you'll find that as a function of the altitude in kilometers, the temperature near the Earth's surface decreases. And then as you reach above the 10 kilometers or 8 to 10 kilometers, which is the troposphere, you'll find that the temperature, after it decreases, it starts going up back again. So there is a reversion in the slope of the curve. You notice here that the temperature would be about 282 degrees, well, Kelvins in that case. And if you take this as a reference value, that would be a concentration of CO2 of 150 parts per million per volume. What if you double the amount of CO2 in the atmosphere, go to those two curves that I have shown you earlier, that would be 300 parts per million per volume. You notice that definitely the prediction is that the temperature of the Earth would go up by about 2 degrees here. And then it goes down, in fact, above the troposphere. So in that case, the heat content basically that comes to us from the sun is constant. So if you heat the Earth at the lower levels, you cool the Earth at the upper level because the heat input is assumed to be a constant. If you quadruple, this is now from 150 parts per million per volume, you go to 600 parts per million per volume, you could see that you get another 2 degrees increase in the temperature near the Earth's surface, but the slope of the curve above the troposphere is going to decrease because of the constancy of the input energy from the sun. Notice here that you have different slopes of the heat movement from the higher level of from the lower level of the atmosphere here, because it's warmer, to the troposphere. And you also get another heat input flow of heat flow. We are going to call it the heat flux because it is governed if you adopt a conduction model according to Fourier laws of conduction. It depends on the slope or the temperature gradient in that case. So what do we do here? We take those lines here, the temperature gradients, in the case of 150 parts per million per volume, in the case of 300 parts per million per volume and 600 parts per million per volume, and not just show it as a graph, we go and see what would be the effect on the heat flows into the troposphere, the net heat flow. We say that there is a heat flow from the bottom, a heat flow from the top, they cancel each other, and the weather phenomena are being done in that troposphere, and we see what is the effect on the heat flux. So we use a very simple model here, as you could see, the different slopes, the initial 150 parts per million, in the below T sub m. We parameterize it so that you can go and plug in numbers and get different results if you wish. R would be the height of the troposphere, where two heat fluxes come in from the top of the troposphere, Q1, and another heat flux comes from the bottom of the troposphere. Now notice that in Fourier equation, the heat flux is a vector. So those two vectors basically cancel each other at the height of the troposphere. We take the initial temperature here as T sub S on the surface, and T sub U there, the surface above the troposphere by a distance S, like shown in the graph that I have shown earlier. We adopt a very simple model without using any supercomputers. The most that we can need in that case is simply a laptop like I'm using here. And basically we apply the Fourier law of conduction, where del square is a Laplacian operator for the temperature as a function of the height z, and that should be equal to 0. Very simple relationship. In that case, you can write it as d squared T of z by dz squared is equal to 0. And we apply the boundary conditions at the height of the troposphere and at the surface of the Earth, and then solve that very simple second order ordinary, it's not even partial, ordinary differential equation. And what the goal is to find T of z, the temperature distribution, as a function of height. And then if you take the gradient of the temperature, you apply the Fourier heat equation of heat conduction for the heat flux. So we are really after, because we cannot really determine the temperature per se, but it's very easy to determine the slope of the curve, and that is the heat flux. So let's see if we do this, what kind of a result we get. You take the equation here, d squared T by dz squared, integrated as a function of height. You have a constant of integration, and you integrate with respect to z, so it becomes C1 of z plus C2. You apply the two boundary conditions, and in that case, you can get the equation for the temperature distribution if you determine what is C1, and if you determine, because it's a second order ordinary differential equation, as you notice, you need two constants of integration, C1 and C2. So if you apply those two boundary conditions, you get basically the distribution of the temperature in one. One would be the region below here. The region 1 is the region above the troposphere. And you also can make a solution for the temperature distribution in the region. This is region 1. I think here we have, we should reverse that 1 and that 2 here, Q sub 1, and that should be Q sub 2. But nevertheless, it's simply the difference that matters between them. So we'll keep going here. We have now a temperature distribution in the lower atmosphere below the troposphere, and we repeat the same process for the temperature distribution above the troposphere. And in that case, you need two other constants of integration, C3 and C4. You're not required to memorize that derivation. You're not going to ask you questions about it, but in that case, you get the temperature distribution in the region 2, which is above the troposphere. Notice it's a linear equation. It's a straight line here. The slope, the temperature as a function of z, the height above the Earth's surface is a function of z, and it's straight line with a constant right here. We are not interested in the temperature distribution per se. What we are interested in is what is the amount of heat that is carried from the Earth's surface to the troposphere, and from above the troposphere to the troposphere where the weather phenomena are done. So in that case, we use Fourier's law on conduction. We admit that we have convection. It's not just conduction, but this is simply a first or back of the envelope type of a first trial calculation. And in that case, we have the temperature distribution. That gradient of the temperature is dt by dz. And here you have to take into account the conductivity of the atmosphere, K. And you have to take also the area of the atmosphere, capital A. But the problem is we don't know what they are. We don't know what is K. We don't know what is A. So now either that we give up or we found a nice trick that you may adopt in the future in any calculation you do. In that case, if you take the ratio, you'll find that the area and the conductivity of the atmosphere cancel out. So what do? We take a reference case for the initial concentration of CO2, the 150 parts per million per volume, and then calculate the other values when you double it, when you double the concentration of CO2, and when you quadruple the concentration of CO2. Notice that in the region number 1 and the region number 2, the heat fluxes are vectors, so they cancel out. So in that case, we can calculate the net heat flux in getting into the troposphere. And the net heat flux, of course, is the energy that the Earth uses in generating tornadoes, hurricanes, even snowstorms and rain events. So the higher the energy that you put into the troposphere, the more energy is available for those weather phenomena in general. So we take some values here and plug it in because we have a derivation of the net heat flux. We take the height of the troposphere as 13 kilometers. You can go and change it yourself. And we take S is 40 kilometers, the area above the troposphere minus the 13, the height of the troposphere. That's 27 kilometers. And we take the T sub M in the graph at 210 Kelvins. So we don't use the degrees Kelvin anymore by convention. You'll find that we can then figure out what is the net heat flux. This is the Q net minus a reference value, which is the 150 parts per million per volume, relative to the initial value. So in that case, we solve the problem in a relative way. We don't worry about the temperature itself. We don't worry about the heat flux itself. In that case, K and A, which we cannot measure, we cannot really, we don't know them, cancel out. And in that case, you get the percentage relative increase in the net heat flux. It's a very simple trick that you may use in deriving equations when some of the variables are not measurable or unknown in general. And this is what we get in a simple table form. If you start with 150 parts per million per volume, you'll find that if you assume the surface temperature is 282 Kelvins, that's 273 plus, of course, degrees Celsius. And you find that from the graph that we started from, if you double it, you increase the temperature by 2 degrees, 2 Kelvins, or 2 Celsius, in fact, 2. If you quadruple it, you add another 2 degrees. So in that case, you can measure, in fact, or calculate the upper level temperatures. You can calculate the temperature gradient, and you get the net heat flux. So this is net heat flux as a reference. You go and calculate the same value at a concentration of 300 parts per million per volume, and you can calculate the net heat flux. And what matters in that case is the ratio between the difference between the 2 heat flux relative to the 3.35. And if you calculate this, if you double the carbon dioxide concentration, the intensity or the heat flux relative increase is 22.4%. So this means that if you allow the global warming to increase the temperature of the atmosphere by 2 degrees by doubling the carbon dioxide concentration, the intensity of storms, all kinds of storms, whether it's hurricanes or tornadoes or ice storms or even droughts, is increased by 22%. If you quadruple from 150 to 600, you end up with 40% increase in the weather phenomena. So as you increase the temperature of the Earth, other than just people being inconvenienced with high temperature, you find that your weather phenomena are going to be much more intense and much more destructive. And in fact, this was done about a few years ago, but the evidence shows that this is happening today. That table can be put in the form of a graph. 150 parts per million carbon dioxide concentration per volume. You'll find that the heat flux increases into the troposphere, the net, meaning the flux from the Earth up and from the above the troposphere down. And you find that the net increase, if you double the carbon dioxide concentration, goes up by 20%. The net heat flux goes up by 40% if you quadruple the carbon dioxide concentration. That was one of the first ever predictions of the increase in the intensity of weather phenomena. And people have tried it, of course, with supercomputer, and it bears really reality. So that is really true. The interesting thing about it is that the fascinating thing about it is that if we don't do something as humans in our contribution to that increase in the temperature, the greenhouse effect near the Earth's surface, if we don't do it ourselves, nature will do it to us. And in that case, it is not under our direct control in general. So what is available to us to try to control the weather phenomena? We go back to this idea of restoring the circumglobal equatorial current. And you'll see how it can be done using our knowledge of nuclear energy in general. As I suggested at the time, archaeological time, the Jurassic time, and the late Jurassic climate, we suggested that the temperature of the Earth was very, very, very mild. We know also that the Atlantic Ocean and the Pacific Ocean were interconnected. Right now, they are not interconnected. This is the Panama Canal. It uses locks. Ships come in from one side, they go into these locks here. The water level is raised by bringing fresh water from a lake there called Lake Gatun. And then the ships travel through a part of the canal that has been dug by humans, but most of the way they travel in a freshwater lake, Lake Gatun. And I'll show you more details that maybe you haven't seen before. This is the Panama Canal map from the Atlantic Ocean right here through that Lake Gatun. Only a small part of the canal has been really dug from here to here. And from here to here, basically, most of the travel is through the lake. You notice also that in that case, this is a profile of the Panama Canal. Notice here that it's the Pacific Ocean. You take the ships, put them into locks, another lock, a third lock, raise them to the level of Lake Gatun. They travel into, it's written here as Gatun Lake. And then when you reach the Atlantic, you go down 1, 2, 3 locks. So it is not a sea level canal. What is the solution if you want to restore the very mild climate that existed the 30 million years ago? So in that case, we adopt technologies that are designated as nuclear civil engineering. It is basically a modification of the Earth, and there are several ways that we can reconnect. Like 30 million years ago, when we had a very mild climate on Earth, the Atlantic Ocean to the Pacific Ocean. It would be a very, very ambitious project. And doing it by conventional methods, digging with basically people or machines, is not going to be economical whatsoever. So what is the suggestion? We have the great power of nuclear peaceful explosives. So in that case, nuclear energy comes into play here. Before I go further, there are several locations that can be considered for that sea level canal. One of here is through Nicaragua. There is one through Venezuela. But the shortest path is through the existing Panama Canal. And I warn here, I suggest that if we do not reconnect the Atlantic to the Pacific in our own way, obviously we have to compensate the people in this area for allowing humanity to benefit, so they should benefit too. The Earth will do it for us. The Arctic ice cap will melt, Antarctica will melt, and in that case, you find that many, many very large areas of the Earth's surface will be flooded. Like, for instance, in Florida would be all underwater. All the cities, Louisiana and so on in the Venice in Italy would be underwater. The delta of the Nile, of the Ganges, of the Mekong River in Vietnam will all be underwater. So these are different areas where we can basically have a sea level canal and restore basically the circumglobal equatorial current that happened a long time ago. So this is a depiction of what we do in that case. We would use nuclear explosives, thermonuclear devices, hydrogen bombs basically, explode them in a single row. If you explode them in a single row, the explosion gases would eject the ground and basically dig for us a long canal, maybe not through the whole length of the Panama area, but from Lake Gatun to the Pacific and the Atlantic. So in that case, we would excavate a sea level canal with a width maybe of 1,000 feet. And if we restore the conditions that existed for the climate 30 million years ago, in that case, the Earth's climate would not run away from us. There have been experiments on using nuclear explosives. This is a 35 kiloton TNT explosive. You could see it forms a crater. As it is exploded here below ground, it ejects the Earth from the surface to both sides. And this is another example of a 2.3 kiloton TNT. That's a fission device, but this is a Sedan crater. Experiments that were done at some point called the Plowshare program. The idea was to build harbors, for instance, or explore for oil, increase the production of oil. But here, if you explode those devices, even in granite, this is a granite experiment, you can really dig a ditch. And this is a simple way of recreating the conditions of the earlier connection between the Atlantic and the Pacific Ocean. I describe here the challenges that you would meet in the case of using civil nuclear engineering. In that case, you need basically to control the activation fallout products from the explosions themselves. So you have to choose the material. I study here, I give you the different isotopes that would be generated. Some of them emit betas, but no gamma rays, like phosphorus 32, but calcium 45 would emit beta particles and gammas with a very short half-life. So you have to choose also materials in the explosive devices that have short half-life. All of them here, as you can see, are hours, days. One of them is iron 55 that would have a half-life of 2.7 years, so it would last a few years in terms of radioactivity. But we can control the materials and the activations, and it becomes a very challenging terraforming project. In the same way as some radiation will leak into the oceans from the locations of the explosions, depending on the tonnage or the yield from the explosives. 1 megaton would basically study it for a small harbor, and for a harbor in Alaska, some studies show that you can get basically fallout in the direction of the wind. The effect of depth of burial is listed here if you find yourself designing such a project. And in that case, this is a way, I'll ask you to read a paper about it and write a summary of it. So if we do not act on and try to mitigate the consequences of global warming. As I suggested, nature will do it itself. And I can show you maybe a graph that shows us the extent of how the low-level parts of the world are basically the whole Earth would become a water world. There was a movie done about it. Other people have been suggesting other ideas other than the idea that I'm presenting here, which is restoring the circumglobal equatorial current. This is supposed to be an artificial tree, and the artificial tree would simply absorb the carbon dioxide from the atmosphere. Some people even suggested other ideas. We suggested that the albedo can cool the Earth's surface. So this is an idea in the British Philosophical Society's publications in what's called the Flettner turbine. This is from wind energy application. If you rotate that cylinder here, you'll find that you can build a ship that moves on the surface of the oceans. Some of the energy produced from the wind power can be used to pump water and eject it into the atmosphere. So what do you do there? You form low-lying clouds. And if you form low-lying clouds, you basically have the albedo effect or the reflection effect from cooling the Earth's surface. That's another approach other than the nuclear civil engineering. Cooling towers can be used to produce more steam, and these are also low-lying clouds. Volcanic eruptions do it for us, whether we like it or not. And in that case, you find that some people even suggest the process of carbon capture and storage. So there is very serious research being done along that line. Now, I warn you about the ideas. This idea needs to be studied thoroughly. So there are opposing points of view to it. So I urge you, if you want to learn about any topic in your future careers, read the two views, the opposing views and the four views, and forget about them and make your own opinion. So here I expose to you the different points of view about climatic change in general. Climatic change is a filter, a big challenge to humanity. Every year they conduct a meeting on trying to discuss what are the methods that humanity is going to use. Justice for a climate of peace. The latest meeting has been the last week, in fact, in Sharm el-Sheikh along the Red Sea in Egypt. And yeah, you notice that if we don't do it, the first people to suffer from it are people living on the islands in the Pacific. This is the Tuvalu Island, simply is disappearing. So those people who live there cannot survive there because some other people are burning coal and methane and petroleum in other parts of the world. And this shows us what, if we do not intervene ourselves as humans, what would be the rising sea level in the United States and the Gulf of Mexico. Look at this. All of Florida here, the cities of New Orleans, Houston, would be all underwater. Veracruz, Cancun in Mexico would be underwater. Port-au-Prince, Haiti, would be underwater. So we are facing a global change in the climate. It is reality. This is, in fact, what happens when they get what's called king tides in Fort Lauderdale in Florida. When they get the tides, as you know, are caused by the moon. So in that case, look at the coastal roads. This is what happens already in Venice, in Italy. You could see that the water, once in a while, when they get those tides, this city, Venice, would be all underwater, and we lose a great part of the habitation of humanity. As I suggested, the intensity of storms are going to become more and more serious, leading to destruction. This is, unfortunately, the cities of paradise. 2 years ago, only 2019, the whole city was lost to fire. And ironically, it is named Paradise. The effects are already being suffered by many, many people. And I'll just show you two heartbreaking kind of pictures. Again, restoring the circumglobal equatorial current is a great project if we can do it. I'll let you read more about it. But some scientists suggest that, in fact, the cycles that we have shown, the 100,000-year cycle, the 34-week cycle, basically reinforce each other. And scientist Valentina Zharkova from the Ukraine suggests that we are really, when you superimpose the cycle, that we are headed maybe into global cooling. So in that case, it's not global warming, but it's global cooling. As I suggest, the intensity of storms are going to be very intensified. This is a picture taken by migrants in the Mediterranean Sea on a boat there asking for help. It won a Pulitzer Prize in photography, and the effects of climatic change are being already lived. These are migrants from the Middle East into Europe. These people on a dinghy trying to reach the Europe, and of course on our south border, people also are migrating. So the effects are leading to global dislocations. Some countries welcome the migrants, some others do not, as you could see here. And humanity is facing a filter that can affect our future. Some people suggest we can build artificial islands, but this is basically artist conceptions. And I'll leave it at this and ask you to read 2 papers and write a summary of them. Everything we cover today, please make sure, and the assignments we'll cover in the tests the next time we meet. And the recordings are going to be placed, as I suggested, in the Illinois media space. I put lots of effort in that and bring it to the attention of other people who might be interested in watching the lecture. That has been an effort that took 2 years consecutively here. There are 7 channels. Each one of them contains about 38 recordings. You could see the effort that was put on it. And I thank the TAs, Anshal and Alvaro, to acting as co-hosts in the recording. And just read the material, work the assignments, and I wish you all a nice Merry Christmas and Happy New Year.